Every time you hit undo, stream a song, or send a document to your printer, you are moving massive amounts of invisible data. To your computer, those features are just gigantic piles of raw information. If you threw all that data into a single, unorganized heap, the system would immediately crash, trying to locate the right piece at the right time. Computer scientists solve this by using data structures. These are specialized geometric formats designed specifically to organize and store information. For linked lists, stacks, and queues, functionality is defined by two basic operations: the rules governing how data enters the sequence and the logic used to remove it. By strictly controlling those rules of entry and exit, we turn digital gridlock into high-speed processing. The most flexible building block is the singly linked list. It stores information in individual units called nodes. Each node holds a specific piece of data along with a pointer. That pointer is exactly what it sounds like: a directional address pointing to the next node in the sequence. They link together from the starting head all the way to a null endpoint. The defining rule of the linked list is total structural freedom. You are permitted to insert or delete data absolutely anywhere in the chain. This graphic shows inserting a new node mid-sequence. Two tracking pointers, PTR and pre-PTR, locate the gap. Then the computer rewrites the addresses. The preceding node points to the new node, which points to the following node. Looking at this technical diagram, we can see the opposite process for deletion. To remove a node, you simply tell the preceding node to bypass the target completely and point its address directly to the succeeding node. This architecture allows for insertion at any point in the sequence, provided the addresses are managed carefully to keep the chain intact. Curious. So what happens if we take that flexible list and strictly seal off one end? You get a stack. Its defining rule is last in, first out, or LIFO. Think of a stack of heavy plates. Pulling an item from the bottom or middle out of order completely destroys the integrity of the pile. Because of this physical constraint, you can only insert or push and delete or pop data from the absolute top of the structure. This strict limitation creates a flawless historical record. It is exactly how your word processor's undo button or your web browser's back arrow perfectly recalls your most recent actions in reverse order. By severely restricting access to a single point, the stack guarantees an accurate chronological backtrack. Now consider a geometric constraint that is open at both ends, but where data traffic flows strictly one way. This is a queue, governed by the rule first in, first out, or FIFO. In a queue, insertions, called in-queue, occur only at the rear, while deletions, DQ, happen at the front. Because memory is finite, if the structure fills completely, new data bounces off, causing a queue overflow. This architecture is built for processing tasks sequentially, exactly how a shared office printer handles multiple document requests in the precise order they were received. The directional flow of a queue ensures that data is processed in its original sequence, preventing any single request from skipping the line. Why do we bother building these specific chains and tubes when standard data arrays, basic side-by-side lists, already exist? Standard arrays are incredibly fast when you simply need to search for an item, but they are incredibly slow for insertion and deletion. If you force a new piece of data into the middle of an array, every single item to its right must individually shift over to make room. In computer science, we measure this using big O time complexity. An array insertion has an O of n time complexity. That means the computer has to execute a time-consuming shift for every single item currently sitting in the list. This animated chart shows the mathematical advantage of our specialized structures. Because linked lists, stacks, and queues rely on swapping address pointers rather than physically shifting data, their insertions and deletions hit a blazing fast O of 1 time complexity. An O of 1 score means the operation is instantaneous and constant. It takes the exact same microscopic amount of time whether your system is managing 10 items or 10 billion items. There is no single perfect way to store information. There are only calculated trade-offs between processing speed and structural flexibility. By understanding these strict rules of entry and exit, programmers act as invisible architects, selecting the exact geometry required to keep the digital world moving without